Hello class, this is Mrs. Ayodeji with today's video on 11.3, the short run behavior of polynomial functions. As you're watching the video, feel free to pause, rewind, or replay the video as often as you need, writing down important formulas, equations, or statements. Feel free to replay the video as often as you need, and at the end of watching the video, write a brief summary of what occurred in the video and submit that summary via the online list form, as well as a top question. All right, let's begin. 11.3 talks about the short run behavior of polynomial functions, and a lot of the questions that you guys had during the 11.2 WISC review could be answered in 11.3, especially what goes on not at the ends of the polynomial functions, but really what goes on in the middle of the polynomial functions. And we're going to talk about that today and how to determine that. All right, let's begin. So in this first example, we all know that long-run behavior is determined by its leading term. However, polynomials with the same leading term may be very different in their short-run behaviors. So what we're going to do is we're going to take a look at 3 degree 4 polynomials, f, g, and h, and there are their equations, and here are their graphs. And as you can see, for this particular window, -10 to 10 for the x values and -500 to 4,000 for the y values, it looks like these graphs look very, very similar. And if we were to, since the leading term of each of these graphs is x to the 4th, if I was to graph x to the 4th power function, as you can see, they look very similar. But what happens when we change the window? Well, they look very similar like they did for this zoomed out window. So as you can see, we change now the window from an x-axis from -5 to 5 and a y-axis from -35 to 15. And as you can see, the graphs look totally 100% different than one another. Okay, so here is the f of x, here's g of x, and here is h of x. So I'm sure the question is, if I have the function, how can I determine the short run behavior? Because I know how to determine the long run behavior from the previous unit section. So let's take a look at how to determine from the polynomial what the short run behavior is. And in order to do that, we're going to look at an example in the book using example 2. The first step is to basically rewrite the polynomial as a product of linear factors so we can easily determine the zeros or the x-intercepts of the function, and then use that to describe the graph fully, like where does it cross the x-axis, hence from the zeros. Where does it cross the y-axis? We can determine that from the original standard form of the polynomial. And where is the function positive? Where is the function negative? And I'll show you the way of the book doesn't show you how to do it, but a more easier way to figure out and determine that. So in this case, we have this polynomial function and it's third degree because the highest power is 3. And as we can see here, there is no constant term, which means that this value right here is +0, which means the y-intercept is at 0. Okay, so when we write this in terms of linear factors, as we can see from algebra, we end up with 3 linear factors, which makes sense because the polynomial is a degree 3. So we have here, once we have each linear factor, if x is a linear factor, that's the same thing as x minus 0. So x equals 0 is a 0. X equals 3 is a 0 because of the linear factor x minus 3. And x equals -2 is a 0 because of the linear factor x plus 2. And so now we have the x-intercepts of the graph. We already know that there is no y-intercept of the graph. There is a 0 y-intercept of the graph. So now the question is, where is it negative and where is it positive? So I'm going to show you this, and then I'm going to explain what I did this. The first thing I did was I set up a number line, and the important points were the zeros in numerical order, -2, 0, and 3. And then I basically broke up the number line into 4 intervals. This interval is all values less than -2. This interval is all x values between -2 and 0. And this interval is all x values between 0 and 3. And this interval is all x values greater than 3. And I picked a point that's in each of the intervals and determined really the sign, whether it's negative or positive. And that will determine what all the values in that interval are going to be. So for example, I picked -4 for x, and I calculated it, and I see that I got a negative number. So that means on the entire interval from -2 to -infinity, I'm going to have negative values. Okay. For the interval between -2 and 0, I picked an easy number, -1, and I found out that that function value was positive. So that means for every x value in the interval -2 to 0, the function values are going to be positive. Okay, I did the same for this interval. I could have picked an easier one like 1, because that's between 0 and 3, but I wanted to be diverse, so I picked this value. And as you can see, it turned out to be negative. And then for the last interval from 3 to infinity, I picked 5, and I saw that it turned out to be positive. Okay? And so now I have an idea of what the graph is going to look like. And because I actually calculated 4 points on the graph, I now know all the x-intercepts in addition to 4 points to help me sketch the graph. Now I want to point out, because 3 is an even degree polynomial and the leading coefficient is a positive number, I already know the end behaviors on the first interval and the last interval, but it's good to evaluate and get extra points. So here are my x-intercepts, i.e. the zeros of the graph that I found earlier, and then here are the points that I found using, oh, you can't even see the other one, sorry, move this out of the way. As you can see over here. So as you can see, now that I have all of my zeros and all of the points from that I did for the interval testing, now I can just sketch them and connect them with a lovely flowing polynomial graph. And as you can see, this is what the graph looks like exactly. Okay, so this is how you use the polynomial in the to determine the short run behavior, by finding the zeros, and then by finding the interval, the y-intercept, which we already knew is 0, and then also finding where the intervals, where the graph is positive, negative, and vice versa. And finding actual points allows you to actually have a better exact sketch of the function. Now some of you may be thinking, that's great because we have the equation, but what if we don't have the equation? What if we have the graph? How can we determine the equation? Well, we're going to talk about that as well today too. Before we do, I want to introduce some terminology that we'll be using to help understand things. So if P is a polynomial, then if the formula of P has a linear factor, and so a linear factor, we've used them before, they look like something like x minus something. Okay, so if P has a linear factor or more than one linear factor, and each linear factor looks like this, then that also means that P has a 0 at this value. I know some of you are saying, oh, I already knew that. And you did already know that it's 0, but this is the term linear factor. Conversely, which means the other direction, if P has a 0 at x equals k, then that means it also has a linear factor of the form x minus k, okay, in the actual equation. So if we know the zeros of the polynomial, we can start building the polynomial equation using these linear factors. And so the question becomes, well, how many linear factors we have? And I'm also going to introduce some other terminology called bumps and turns. Okay, so this is very important. It says that the number of linear factors of a polynomial is always less than or equal to the degree of the polynomial. Okay, and I know some of you are saying, what does that mean and how do we know? Well, how do we know? You'll find out in calculus, but just know and trust me that the number of linear factors of any polynomial is equal to a number less than or equal to the degree of the polynomial. So in the previous example, we had a third degree polynomial and there were exactly 3 linear factors, x minus 0, x minus 3, and x plus 2. Okay, so also, between any 2 consecutive zeros, in other words, zeros that are on a number line right next to one another, there is at least one bump. And I know some of you are saying, what do you mean by bump? So over here we have these are 2 consecutive zeros, -2 and 0. And here we have this bump or hill. And over here we have another set of consecutive zeros, 0 and 3, and we have another bump, or in this case, a valley. Okay, so that's what that means in that situation. So now that we have that information, then here's another pattern. You just have to trust me and you'll find out later in life probably in calculus why this works. It says the graph of an nth degree polynomial has at most n zeros and turns at most n minus 1 times, which means it changes direction when we say turn. Okay, so let's take a look at the example. Earlier we had in example 2 this example of the graph that we were able to sketch using the short run behavior, and in this case it's third degree and it has at most 3 zeros. In this case it has exactly 3 zeros, and the number of turns is 3 minus 1, which is 2, and as you can see here it's increasing and then it changes direction, so that's 1 turn, and then it's decreasing and change directions and it's 2. So it has at most 2 turns, and this supports that. Looking at the very first example we talked about, with the fourth degree polynomials, we had 3 different functions, f, g, and h, and as you can see here, f, g, and h, it had, f had, even though it was fourth degree polynomial, which means it has at most 4 zeros, this one actually has only 2, whereas g has exactly 4, and h has exactly 3. So it does support that it has at most 4 zeros, and then it says it turns at most 3 times. Okay, so this one turned actually 1 time, this one turned 1, 2, 3, I'm sorry, 1, 2, 3 turns, and then this one had 1 turn, 2 turns, 3 turns. Okay, I should have put turns, multiply. Okay, so this right here is very important for you to understand this relationship between these two. Okay, so there's another term we're going to introduce. It's the concept of multiple zeros. Okay, and we're going to be using this all throughout this course as well as when you get into calculus. So here we have a function, a polynomial function, and it also looks like a power function with a horizontal shift. And as you can see, the degree is 2. And we have a linear factor of x minus 4, which means we have a 0 at 4. But we call this a double zero because of the squared, we actually have 2 linear factors of x minus 4 and x minus 4. So that means that the 0 is actually a double zero. And this is what the graph of that function looks like. Remember I said it was a power function with a horizontal shift. In another case, we have a function, another power function shift, but this is a degree 3 polynomial, and we call this 0, x equals negative 1, a triple zero, because we have 3 linear factors of x plus 1, x plus 1, x plus 1. So that means it's a triple 0. X equals negative 1 is a triple zero of t because of that. Okay, so what does that mean and how does that affect our short run behavior? As you can see, these graphs look very different, and you can just say, oh, because one is an even degree polynomial and one is an odd degree polynomial, but that's thinking long-term behavior. So this is important to understand. If a polynomial with a repeated linear factor, then P has a multiple 0, and you can have a polynomial can have more than one multiple zeros. And if the linear factor occurs an even number of times, then the graph does not cross at the x-axis, but it bounces off the x-axis. As we saw here, this was a double zero, which means it's an even multiplicity, and it bounces off at that double zero point. But if the linear factor occurs an odd number of times, then the graph actually will cross the x-axis instead of bouncing off. And we see that here with x equals negative 1 being a triple zero. Okay? Let's take a look back at the very first example, and let's take a look at what kind of zeros we had. So here we have a flattened 0 at x equals negative 1 and x equals, I think, 2. In this case, because we have a fourth degree polynomial and we have flattened zeros, then it seems like we can have a linear factor of x plus 2 and x minus 2, but one of them has to have a power of 3 and one of them has to have a power of 1, so we can have at most a fourth degree polynomial. Over here, we can see, okay, over here in this graph, which is g of x, we can see we have 4 zeros, which makes sense because it's a degree 4 polynomial, so it can't have more than 4. And all the zeros are flattened zeros, which means that their linear factors have an odd power, which makes sense because the odd power must be 1 for each of these. Okay? And over here for this graph, we have an actual multiple 0 because we have a bounce and then 2 flattened zeros. So since this is a degree 4 polynomial, then that must mean this linear factor or 0 must be a multiple 0 with a power of an even number, 2 or 4 or 6. But since this is a 4th degree polynomial, then this linear factor should have a power of 2, where each of these have a power of 1. Okay, so this last concept, I know this video is long, but it's not going to be longer than 17 minutes because this is a really important chapter. We're going to find the formula for a polynomial just from its graph, okay? So in this case, we have this function, as you can see right here, and we're going to describe the long-run behavior and the short-run behavior to start building the function for its graph. As you can see, as x goes to infinity, the function value goes to negative infinity. And as x goes to negative infinity, the function value goes to positive infinity, which means that the degree of this polynomial has to be odd and bigger than 1, and also that the leading coefficient has to be negative, because if not, then these would be switched in direction. From the short-run behavior, we see that it has two terms, 2 zeros, one at x equals negative 1, which is a flattened 0, and one at x equals 3, which is a bump. So that means that the linear factor in the polynomial is x plus 1, and it has to have an odd multiplicity, and the linear factor at x minus 3 has an even multiplicity. So we can come up with this expression simply because of what we said up here. And we also know that k is negative. Now, this is not the only expression. This is just one of many that can fit this situation. And because the y-intercept is at negative 3, we have this. And we solve this. So we solve for k, and this is our possible formula. All right, that's it.